When stars die, the universe is transformed in ways both beautiful and violent. These are the universe's most dramatic moments, spectacles of unimaginable energy and scale, unfolding over thousands or even millions of years. Imagine yourself floating in the vast emptiness of space, watching a star that has burned for billions of years suddenly begin to change before your eyes. The star swells, its color shifting from a brilliant white-hot to a deep glowing red, growing ever larger until it engulfs everything in its path, including any nearby planets. Or picture a massive star collapsing under its own gravity, then erupting in a supernova, an explosion so bright it can outshine an entire galaxy for a brief moment. These are the real, awe-inspiring finales of stars across our cosmos, each one unique and powerful in its own right. The life of a star is a delicate balance between gravity pulling inward and the force of nuclear fusion pushing outward, creating a dynamic tension that lasts for eons. But eventually, the star's fuel is exhausted, and gravity begins to win, pulling the star inward and starting its final, inevitable journey toward death. From the quiet, gentle fading of stars like our sun to the violent, cataclysmic explosions of supernovae, the death of a star is always a profound and moving event. In dying, stars scatter their enriched elements across the cosmos, seeding the universe with the building blocks for new stars, planets, and even life itself. So let's explore what truly happens when stars reach their spectacular and inevitable end. Let's start with a star like our sun, a seemingly eternal beacon in the sky. For most of its life, a small star is in its main sequence, fusing hydrogen into helium in a stable, ongoing process. This fusion releases energy, the light and heat that makes life on Earth possible, bathing our planet in warmth and light. But eventually the hydrogen fuel is exhausted, and gravity begins to compress the core, leading to dramatic changes. This compression heats the core, igniting a shell of hydrogen around the helium core, creating a new source of energy. The star swells into a red giant, growing 100 times its original size, a truly colossal transformation. If this were our sun, it would engulf Mercury, Venus, and possibly Earth, dramatically altering our solar system. The core contracts and heats up further, igniting helium into heavier elements like carbon and oxygen, essential building blocks of life. Once the helium is used up, the star becomes unstable, puffing its outer layers into space in a series of gentle but powerful waves. These expanding shells create a planetary nebula, a glowing smoke ring of ionized gas that lights up the cosmos. At the center is the star's core, now a white dwarf, an incredibly dense object, the remnant of a once mighty star. It no longer produces heat through fusion. It's a stellar ember, glowing with leftover energy, slowly cooling over time. The white dwarf is the final stage, slowly cooling and fading over trillions of years, a process that takes an almost unimaginable amount of time. For a star like our sun, the end is a slow, graceful process, a serene conclusion to a long and stable life. It's a long goodbye that enriches the universe, leaving behind a nebula and a dense remnant, contributing to the cosmic cycle. It's a quiet end, but one that is profoundly important for the cosmic cycle of birth, life, and death, ensuring the continuity of the universe. Now let's turn our attention to the true giants of the cosmos, massive stars, those that are at least 8 times more massive than our sun. These stellar behemoths are rare, but their lives and deaths shape the universe in dramatic ways. Massive stars live fast and die young, burning through their nuclear fuel at a breathtaking pace. While our sun will shine for billions of years, these stars exhaust their fuel in just a few million years, a cosmic blink of an eye. Deep in their cores, massive stars fuse hydrogen into helium at a ferocious rate, producing immense energy and shining with a brilliance that can outshine thousands of ordinary stars. When the hydrogen in the core runs out, gravity takes over, causing the core to contract and heat up. This intense pressure ignites helium, which then fuses into heavier and heavier elements. This process repeats, building up layers of different elements like an onion, with each shell fusing a heavier element than the one before. Eventually the core becomes iron, the end of the line for fusion. Iron cannot release energy through fusion, so the star faces a dead end in its nuclear journey. Fusing iron actually consumes energy, so the core can no longer support itself. In a fraction of a second, the core collapses under its own gravity, setting off a catastrophic chain reaction that triggers a supernova. The collapsing core rebounds, creating a powerful shock wave that rips through the star, tearing it apart in one of the most violent explosions in the universe. This is a supernova, a cosmic event so bright it can outshine its entire galaxy for weeks or even months, visible across vast distances in space. The explosion forges elements heavier than iron, like gold and platinum, and blasts them into the cosmos, seeding future generations of stars and planets. If the original star was between 8 and 20 times the Sun's mass, the core is crushed into a neutron star, a city-sized object with unimaginable density and powerful magnetic fields. But if the star was even more massive, the core collapses further, forming a black hole, an object with gravity so intense that not even light can escape its grasp, marking the ultimate end for the most massive stars. The universe has even more extreme ways for its most massive stars to die. A hypernova occurs with stars over 40 times the Sun's mass, forming a rapidly rotating black hole. This setup generates powerful jets of plasma, creating a gamma-ray burst. These bursts are the brightest electromagnetic events in the universe. If a star is so massive that not even a hypernova is possible, it leads to a failed supernova. The inward pull of gravity overpowers the shockwave and the star vanishes. The star disappears, swallowed by the black hole it created. Detecting a failed supernova is challenging. Astronomers look for missing stars. These extreme cases remind us that the universe is full of violent and strange processes. They create the most extreme objects we know of and challenge our theories. We've seen the two great paths a star can take at the end of its life. Small stars fade away, forming planetary nebulae and leaving behind white dwarfs. Big stars die in spectacular explosions, triggering supernovae and leaving neutron stars or black holes. In both cases, their deaths are not just an end but a crucial beginning. These cosmic finales are the universe's recycling program. The debris of supernovae seeds the interstellar medium with elements heavier than hydrogen and helium. The carbon in our DNA, the oxygen we breathe, and the iron in our blood were forged in stars. The death of stars makes new life possible, creating raw materials for new stars and planets. It's a continuous cycle of creation born from destruction. These events connect us to the grandest story of all, the story of the universe.